I welcome you all for this lecture series on deep learning. In this lecture, we will briefly discuss about stochastic autoencoders and decoders. First, we should know what are stochastic encoders and decoders, how it differs from the normal autoencoder. First, the stochastic autoencoders introduce randomness into the encoding and decoding process. The stochastic autoencoders are advanced neural network models that introduces randomness in both the encoding and decoding stages. Unlike traditional autoencoders that always produce the same latent representation for the given input. Whereas there is stochastic autoencoders incorporate probabilistic sampling. This randomness enables the networks to capture uncertainty and variations in the input data. As a result, the model becomes more flexible, learns richer feature representations, and performs better on complex datasets with diverse patterns. Unlike deterministic autoencoders, the encoder outputs a probability distribution rather than a single latent value. So, in the deterministic autoencoder, the encoder compresses the input into a single latent, fixed latent vector. However, in stochastic autoencoders, what will happen means the encoder predicts the parameters of a probability distributions, usually the mean, mu, and variance sigma square instead of a fixed value. This probabilistic representation allows the model to capture the uncertainty present in the data and provides a continuous latent space where similar inputs are represented close to each other. Consequently, the model learns more informative and robust features. So the latent representation is sampled from the learned distribution. Once the encoder learns the probability distribution, latent vector is randomly sampled from that distribution instead of using fixed representation. This is the main advantage of using this stochastic encoders. The sample latent vector contains the compressed information about the input and is passed to the decoder for reconstruction. Since different samples can be drawn from the same distribution, the model can generate multiple meaningful representations of similar inputs. This capability improves diversity in generated outputs and enhances the flexibility of learning process, and it improves the generalization and robustness. Stochastic autoencoders improves the model's ability to generalize to unseen data by learning distributions rather than memorizing the exact input-output mappings. The probability latent space prevents overfitting and allows the model to reconstruct inputs. So they contain noise or missing information. This makes stochastic autoencoders more robust than deterministic autoencoders, especially when working with real-world dataset that often include uncertainty and imperfections, and it forms the foundation of variational autoencoders VAEs. How it forms the foundation for VAEs. Stochastic encoders and decoders are fundamental building blocks of variational autoencoders. VAEs use probabilistic encoding. VAEs use the probabilistic encoding process, latent variable sampling, and probabilistic decoding to learn smooth latent representations of data. These models are capable of generating realistic images, detecting anomalies, reconstructing incomplete data, and learning meaningful feature representations. Due to the capabilities, VAEs are widely used in computer vision, medical imaging, natural language processing, and many other artificial intelligence applications. The equation is given by Z is equal to Q of Z given X. The X is the input data, where X is the given input data, Z is the latent variable, and Q of Z comma X is given X is the probability distribution that is learned by the encoder. So this equation indicates that the latent variable Z is randomly sampled from the probability distribution Q of Z given X learned by the encoder for a given input. What is the input given? Input is X. Here, X represents what? Input data I said. Z denotes the latent representation, and Q of Z comma S is the conditional probability. Here, given, Z given A. It is the conditional probability distribution estimated by the encoder. Instead of assigning a fixed latent vector, the encoder learns a distribution that captures both important features and the uncertainty present in the input data. The probabilistic sampling enables stochastic autoencoders to generate diverse outputs and improves their generalization ability. Next, the comparison between deterministic versus autoencoders, and here it uses the fixed latent vectors deterministic, whereas stochastic encoder uses the random latent vectors. And here same output for every time, and it uses the different sample possible. Different sample possible means what? Because deterministic autoencoders use a fixed latent representation, they always reconstruct the same output for the same input. Whereas the stochastic autoencoders, however, sample different latent vectors from the learned distributions, allowing the decoder to generate slightly different but realistic outputs for identical inputs. This ability is particularly useful in generative tasks where producing diverse outputs is more valuable than obtaining a single deterministic reconstruction. And here it uses the less robust, and it is more robust in the sense deterministic autoencoders often struggle with the input data contains noise or uncertainty because they rely on fixed latent representation. Whereas in the stochastic autoencoder models, uncertainty explicitly using probability distributions, making them much more robust to noisy, incomplete, or corrupted input. This randomness, so this robustness enables the model to produce reliable reconstructions even under challenging conditions and improve overall prediction accuracy. And it uses the simple architecture, it uses probabilistic architecture. So the architecture of the deterministic autoencoder is relatively simple because it directly maps the input to a latent vector and reconstructs the output. In contrast, stochastic autoencoders incorporate additional components such as mean and variance estimation, latent variable sampling, and probabilistic decoding. Although this probabilistic architecture increases computational complexity, it significantly improves the model's learning capability and generative performance. And here it uses the limited data generation, whereas it uses excellent data generation. Deterministic autoencoders mainly used for feature extraction and input reconstruction, making them less suitable for generating new data. Whereas stochastic encoders, autoencoders, learn a continuous probabilistic latent space that enables them to generate new and realistic samples by simplifying the drawing different latent vectors from the latent learned distribution. This capability makes them highly effective for image synthesis, data augmentation, content generation, and anomaly detection. So these are all the advantages of stochastic models. It handles uncertainty and it is better for latent representation. It supports generative learning. And the next is the stochastic encoder. Then we'll see a decoder. And the working of the stochastic encoder is given by this is the processor. The input image enters the encoder, that I'll show you the diagram. And here the stochastic encoder begins by receiving the input image or input data and passing it through several layers of neural network. These layers automatically extract important features such as edges, textures, shapes, and patterns while reducing dimensionality of the data. The encoder compresses the high dimensional input into a lower dimensional latent representation that retains the most significant information required for reconstruction. This feature extraction process enables efficient data compression while preserving essential characters of the input. And the encoder predicts the mean represented by mu. Instead of generating fixed latent vector, the stochastic encoder predicts the mean mu of the latent probability distribution. The mean represents the central value of or expected position of the latent representation for the given input. It captures the most likely features learned by the encoder and serves as one of the key parameters defining the Gaussian distribution. During training, the network learns the optimal mean value that best represents the input data, and the encoder predicts the variance. Along with the mean, the encoder predicts the variance sigma square, the of the latent distribution. The variance measures the uncertainty or spread of the latent features around the mean. A larger variance indicates greater uncertainty in the representation, whereas a smaller variance indicates that the encoder is more confident about the learned features And predicting both mean and variance enables the network to model uncertainty effectively and improves the robustness of the learned latent space. And here the random sampling generates generates the latent vectors. And once the encoding predicts the mean and variance, the latent vector is generated by randomly sampling from the corresponding Gaussian distribution instead of using the fixed latent representation. The stochastic encoder selects the different latent vectors during training based on the learned distributions. This sampling introduces controlled randomness into model, allowing it to explore multiple latent representations for similar inputs and improving its ability to generate diverse outputs. And latent vector carries the probabilistic information. The learned latent vector contains compressed information about the input data together with its uncertainty. Unlike deterministic latent vectors, which represents only fixed features, the probabilistic latent vector captures both the important characteristics and the variable present in the data. This richer representation allows the decoder to reconstruct the input more accurately while also enabling the generation of new and realistic data samples. And this is the mathematical representation. Q of z given x is given by n of mu comma sigma square. This equation indicates that the latent variable z follows the Gaussian normal. N means normal distribution. Conditional on the condition on the input x. Input x. Here the encoder predicts the two parameters of the distribution, the mean mu, and which specifies the center of the distribution, and variance sigma square, which determines how widely the latent values are spreaded around the mean. Instead of producing single latent vector, the encoder learns this probability distribution and sampling latent vectors from it. This probabilistic representation enables smoother latent space, improved generalization, and realistic data generations. So this is the architecture diagram of the input image is being given here. This is the flow of the architecture of the encoder. The architecture of the stochastic encoder begins with the input image, which processed by the neural network encoder to extract meaningful features. The encoder then predicts what it will predict. What I have said, mean and variance. The encoder, what is the function of the encoder? That predicts two outputs. What are they? Mean and variance, sigma square, and which together define the latent Gaussian distribution. Using these parameters, random sampling process generates the latent vector Z. This sampled latent vector represents a compressed probabilistic representation of the input data and is forwarded to the decoder for reconstruction. By learning a distribution instead of fixed representation, the encoder captures uncertainty, improves robustness, and supports the generation of diverse outputs. Next, represent reparameterization trick. Here we need to go for the reparameterization. The problem is random sampling block gradient propagation. During training, neural networks use backpropagation to update their weights by calculating gradients. However, random sampling operation used in stochastic autoencoder is not differentiable, meaning a gradient, that is meaning that gradients cannot pass through it. As a result, the encoder cannot be trained directly using the conventional gradient based optimization techniques. This limitation creates a major challenge in training stochastic models efficiently. Next, backpropagation cannot optimize the random operations directly. Backpropagation required every operations in the computational graph to be differentiable. Since random sampling introduces unpredictable values, it breaks the gradient flow between the encoder and decoder. Without a different sampling mechanism, the encoder parameters such as the mean and variance cannot be updated effectively during training, preventing the model from learning meaningful latent representation. And the solution, how we are going to overcome these two problems are, we are going to use reparameterization trick. To overcome this problem, stochastic autoencoders use the reparameterization trick. Instead of sampling directly from the learned distribution, the latent vectors is expressed as a combination of the predicted mean and the predicted standard deviation and random noise drawn from the standard normal distribution. This reformulation separates the randomness from the learning parameters, allowing gradients to flow through the network while still preserving the stochastic nature of the latent representation. And this is the equation is given by z is equal to mu plus sigma epsilon, where epsilon is the normal distribution of the value between 0 and 1. So it represents the representation trick used to stochastic autoencoder and variational autoencoders. Mu is, you know, that mean predicted by the encoder. Sigma is the standard deviation that varies, and sigma epsilon is the random noise sampled from the standard normal distribution n of 0 comma 1, the value between 0 comma 1. The latent vector z is generated by scaling random noise with the standard deviation and shifting it by the mean. The mathematical formulation allows the sampling process to remain differentiable, enabling efficient gradient computation and end-to-end network training. And the benefits are it allows the gradient computation, enables end-to-end training, and it is used for stable optimization. The reparameterization trick provides stable and efficient optimization by separating randomness from the learnable network parameter. This leads to smoother convergence during training, reduces optimization instability, and improves the quality of the learned latent data space. Consequently, the model achieves better reconstruction accuracy and generate more realistic outputs. And this is the simple diagram mean. So here the representation diagram illustrates how the latent vector is generated with the interrupting the learning process. The encoder first predicts the mean, then that is mean and the standard deviation. uh, Okay, the random noise epsilon is represented independently sampled. Epsilon is independently here, independently sampled from the standard normal distribution. The noise is multiplied by the standard deviation and added to the mean and producing the latent vector z to the equation. This formulation preserves the randomness required for stochastic learning while allowing gradient to pass through the network and making the sampling operation compatible with the backpropagation and enabling efficient end-to-end training. The main drawback is if you are not able to cope up with the backpropagation, we are going for this trick. And next, the stochastic decoder, just opposite. It receives the sample random vector and generates reconstructed input and learns probability distributions of the output and produces multiple realistic outputs. That means since different latent vectors can be sampled from the learned probability distribution, the decoder can generate multiple realistic output even for the same input. Although these outputs may differ slightly, they retain the essential characteristics of the original data. This property makes the stochastic decoders highly useful for image synthesis, content generation, and data augmentation applications. This is the probability model. The probability of x given x is that is the latent variable, and it represents the conditional probability reconstruction of the original input x from the latent variable z. It defines the how the decoder converts the compressed latent representation back onto the original data space. During training, the decoder learns this probability distribution so that it can generate accurate and realistic reconstruction while preserving the probabilistic information learned by the encoder. And this is the architectural diagram of the decoder. Here, the stochastic decoder architecture begins with the latent vector obtained from the stochastic encoder. This latent representation is passed through the neural network decoder, which process the compressed features and estimates the probability distribution of the reconstructed data. Based on this distribution, the decoder generates the reconstructed image, which should closely resembles the original input. So it is approximately. This architecture enables the decoder to reconstruct accurate image while supporting the generation of multiple realistic output from the different latent samples. And this is the complete stochastic autoencoder architecture: input image, encoder network, mean and variance, reparameterization, latent vector, and decoder network, and reconstructed image. So, and these are all the feature. It learns the probabilistic latent space, it generates diverse outputs, and it handles the uncertainty effectively, and it's smooth latent. It produces the smooth latent representation. That means the regularization introduced during the training, and it encourages the latent space to remain smooth and continuous. And the loss functions which we are using, two loss functions are minimized simultaneously in this work. So in this autoencoder and decoder, stochastic two losses are minimized simultaneously. What are they? Reconstruction loss and KL divergence loss. So the stochastic autoencoder is trained by minimizing two complementary loss functions simultaneously. The reconstruction loss ensures that the reconstructed output is similar to the original data, while KL divergence loss regularizes the latent distribution. Optimizing both losses together allows the model to achieve accurate reconstruction and learns a meaningful probabilistic latent space. First is the reconstruction loss, and it measures the similarity between the input and the output. So reconstruction loss, the difference between the original input and reconstructed x cap is the reconstructed output generated by the decoder. Here it has to, if input is matching with the output, the error should be minimum, most probably it should be 0, but it will not be getting 0. It is commonly calculated using mean squared error, MSE, or binary cross entropy, BCE, and depending on the application. A smaller reconstruction loss indicates that decoder has successfully preserved the important features of the original data during the reconstruction. This we know that. KL divergence loss. It regularizes the latent distribution. KL divergence means how closely the latent distributions matches a predefined prior distribution, and usually standard normal distribution. So that is equation is given by the losses reconstruction plus DKL. DKL given Q of P, Q of Z given as this with the P of Z. That means this equation measures the divergence between encoder learned distribution Q of given X and the prior distribution. This it represents the prior distribution. Minimizing this divergence ensures that the learned data space remains well organized and suitable for generating new data sample. So the total loss is given by reconstructed loss plus divergence, KL divergence loss. Is obtained by combining the two losses. Reconstruction loss focus on accurate reconstruction, while KL divergence ensures smooth and continuous latent representation. Together, these objectives allows the network to balance reconstruction quality with effective probabilistic learning. The benefits are, these are all the applications. Benefits are better feature learning, continuous latent space, and improved generalization. See, these are all the applications. In computer vision, it is being used for image generation, face synthesis, and image reconstruction. And in the medical imaging, MRI enhancement, disease reduction, and normal removal, this encoder decoders are used. This concept, natural language processing, text generation, there is sentence embedding, machine learning translation, it is being used. In the robotic application, sensor modeling, state estimation, model the motion prediction, it is being used. And in the speech processing, it is used for voice generation and speech enhancement. It is being used. So this is the application diagram: stochastic autoencoder, image generation, medical data diagnosis, and NLP text generation. Next, advantages and limitations conclusion. These are all the advantages. Learns probability distribution, generate diverse samples, better generalization, handles noisy data, smooth latent representation, robust feature extraction. The limitations are, it is used, that is complex training process. Training is very complex. It requires more computational. It is very sensitive to hyperparameters. The sampling introduces the variance. These are all the main drawbacks. So this is the entire flow chart of this stochastic autoencoder and decoder. Suppose if you are taking the image like this, here we are feeding into the embedding into the encoder. Here mean and variance are extracted, and here we are using the parameterization technique, and then we are taking the latent vector. Then we are doing the just opposite to this process, decoder process, and we are reconstructing the data. And coming into the conclusion, the first one, the stochastic encoders and the decoders extends traditional autoencoders by learning probability distribution instead of fixed latent vectors. This allows the model to represent uncertainty while preserving important data architecture. And by sampling latent vectors from the latent, that is learned probability distribution, stochastic autoencoder generates the diverse and realistic outputs while maintaining high reconstruction accuracy and strong generalization performance. The representation trick makes stochastic sampling differentiable, enabling efficient end-to-end training through gradient-based optimization without interrupting backpropagation. The final conclusion is these concepts form the foundation of VAE, Variational Autoencoder, one of the most important generative deep learning model. VAEs are widely applied in image generation, anomaly detection, medical imaging, natural language processing, and representation learning, and many other artificial intelligence applications due to their ability and learn meaningful probabilistic latent spaces. Hope everyone understood about the stochastic autoencoders and decoders. The remaining things we'll discuss in the next lecture. Thank you.